Welcome to the channel, everyone. Before the May June 2025 session exams begin, the goal here is to complete the syllabus of Computer Science 9618 as advised by the syllabus. So this won't be a crash course kind of a thing. This is for you to cover the whole syllabus before the exams begin. And we don't have much time remaining, so let's get the syllabus started. Okay. Let's begin with the first part of the syllabus, information representation. Now, this section of the syllabus demands that we have a basic understanding of number systems. We also understand the difference between various prefix that's used in computer science and our standard scientific domain. We also understand the various ways in which binary numbers are represented, such as binary coded decimal. And we also understand the difference between signed and unsigned binary number. So, without any wait, maybe we should get started. So, before we start, I would like to ask a fundamental question. Have you ever wondered why do we use binary number system in computers? What was the necessity to start something completely new? Why 0 and 1? 0 and 1, a binary number system, right? And it corresponds to the base 2, meaning the base usually denotes the number of digits it can hold. So basically, meaning all the numbers that are made by the binary number system are basically in fundamental level made up by either 0 or 1. So why 0 and 1? Well, computers, they're made up of transistors, and transistors can either carry out a flow of current or electricity, or they cannot. And transistors can be in two states only. So a state where electricity or electrons are flowing, or they're not. Basically, 0 representing a state where electrons are not flowing, and 1 representing the flowy state of electrons. And since the fundamental working building block of all our modern technological equipments lie in transistors itself, they could be only in two states. This is why it was absolutely important to introduce a number system that could represent those two states. This is why we have the binary number system. Right? Now, Denary number system. Denary number system is basically our day-to-day number system. It contains digit starting and including 0 to ending and including 9. So it has 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is why it's called Denary number system. We also have another number system that we need to understand, that is hexadecimal number system. Hexadecimal number system has base 16, so basically it has all the digits or values of Denary number system, that is 0 to 9, with an addition of alphabets A, B, C, D, E, F. When we add 0 to 9 is 10, plus A, B, C, D, E, F is 6, gives us total of 6 character values that is represented by hexadecimal number system. All the rudimentary fundamental calculations in our processors are done by binary number system. This is barely visible to the programmer or the user. And above that level comes hexadecimal number system. Now, any person working in networking or working in digital marketing, where they have to use various color codes, yes, RGB codes, they are quite acute with hexadecimal values. All our color codes are basically combinations of red, blue, and green, and these color codes are represented in terms of hexadecimal. So whenever you see 2, 2, 3, 3, 5, F, such as characters in a color, realize that 2 hexadecimal values have been allocated to each of the primary colors, red, blue, and green, or RGB. And 0 to 9 are the numbers which is visible to the programmer or the user. So this is our front-end number system, let's say. So this is a basic introduction to the number system. Now the syllabus demands us to carry out calculations for each of the number systems. So let's proceed towards calculating the various values, converting binary to denary, denary to binary, binary to hexa, hexa to binary, denary, etc., etc. So one specific character of binary number system is called a bit. So 1 is a bit. This is a 1-bit binary number system. This is a 2-bit binary number system. This is a 3-bit binary number system, and this is a 4-bit binary number system, also called as a nibble, N-I-B-B-L-E. And when I add 4 more digits here, meaning it has 8 bits total, we call it a byte. And from byte we have kilobyte, megabyte, gigabyte, petabyte, etc., etc. So the goal here is to convert this. Initially, let's do the 4-bit number system, 4-bit number, binary number, into a base 10 number, which is a denary system. So we use a base 2 and raise its exponent or power to the position of the bit, meaning we have 1 0 1 0. Now we multiply this by 2 and we add all the digits. So basically sum of products of base and its power. Now how do we decide on the power? The position the bit lies in. Since we're only considering the first half of this bit, this is position number 0, this is 1, this is 2, and this is 3. So this gets a power of 0, this gets a power of 1, this gets power 2, this gets power 3. What do we have? 2 to the power 3 is 8, 2 to the power 2 is 4, times 0 is 0, 2 to the power 1 is 2, times 1 is 2, and this is 0. So the number or denary number which this bit represents is 10. Now, whenever you are well equipped with the calculation, you could do this mentally as well. So if you can remember the order of the bits, the order always looks like this. The first position is 1, 2, 4, 8, 16, 32, 64, and 128. Right? So it's basically multiplying by 2. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, and 64 times 2 is 128. So, using a mental model, let's try to directly convert this 8-bit number into a denary number. So, this gets power 1. Value 1. Now it's at the end we need to multiply it by 0, so we don't need to consider this. The 2 is skipped. Next comes 4, next comes 8, the 16 is skipped, next comes 32, the 64 is skipped, the next comes 128. Now remember, I haven't talked about signed and unsigned binary number, so we don't need to consider the sign. And if you see, whenever we add bits, the leftmost side carries the highest value. So the leftmost digit is always going to be of a high importance. It's the highest value carrying bit. So now if we sum it, 128 plus 32 plus 32 plus 8 is 40, 40 plus 128 is 168, plus 4 is 172, plus 1 is 173. So this is the value of our bit. This is how we can calculate the denary value of a binary number in our head as well. Now, what if we need to do the reverse process of this? Well, you could also carry out a mental model similar to this, but an easier model looks like this. So let's say I want to convert this 73 denary value into a binary value. What do? I try to factorize it by 2. So 2 3s are 6, this goes here, 2 7s are 2 6 are 12, and we have one remainder we have 1 as a remainder remaining, so we write it down here. 2 18s are 36, no remainder, so 0. 2 9s are 18, no remainder, so 0. 2 4s are 8, 1 remainder, so we write it here. 2 2s are 0, 2 1s are 0. Now you write down the digit like this in this order. So we have 1 0 0 1 0 0 1 1 2 3 4 5 6 7. Now it's a standard norm to write bits in a byte form, so we may add 1 0 ahead, and we have the 73 denary number in our binary system. Now if I had to do this mentally, remember it's not necessary to have the ability to calculate the numbers in your mind, but it definitely helps you do the calculations quicker, saves you time. So if I had to calculate the denary value of, let's say, 108, right, I would think of the highest number in our combination of numbers, that is 2 4 8 16 32 64 128, that could be added. So that must be less than the number, so the number would be 64, right? Now if I think another least number, if I add 64 plus 32, this becomes 96. I could add that as well. We have 96. Now the goal is to come closer to the 108. So if I add 8, this becomes 104. And if I add 4, this becomes 108. So all the remaining values will be 0. Sorry, 4. Now 2 is 0, 1 is 0, 128 is 0. So 0, 1, 1, 1. Okay, 16 is also 0. I missed 16 here. So here is 1, 0. And 8, 4, 2 is 0, 1 is 0. So our full byte looks like 0 1 1 0 1 1 0 0, right? If I try to convert it, let's see if this works out. This is 1 2 4 8 16, no, 16 32 64 plus 4 plus 8 12 12 plus 32 is 44. 44 plus 64 is 108. This is a mental way you could calculate the binary value from a denary number. Now before proceeding with hexadecimal calculation, I would prefer to introduce you all to a system of binary notation called binary coded decimal. We will come to the prefix part as well. So a binary coded decimal is a process of representing numbers where we represent them in a collection of 4 bits or nibbles. So a number, for instance, 1, if I had to represent this in binary coded decimal, I could have written 0 1 1 1 0 0 1 1, so 2 nibbles. Or it could also be written in a byte form, but make sure whenever you're calculating, the byte must only be calculated to the 4th position only. So 0 0 0 0 0 1 1 1 0 0 0 0 0 0 1 1, and we just take this value and this value and combine them together. We don't add them, we just combine them, meaning 1 2 4. So this is 7, 1 2, this is 3. So the number represented by this is 73. Now, why do we use binary coded decimal? Well, whenever we are representing various digits in our, let's say, plotter display, temperature display, calculator display, it is a wiser decision to choose binary coded decimal, as it saves memory and calculation or power, as it saves the power and processing power of our CPU. So this is basically binary coded decimal. Make sure you're just using 4 bits. Make sure you read the questions properly if it mentions binary coded decimal or not, and then you proceed with calculating the value of 4 bit and you combine them and write as a single unit. Now, since we're in the flow of binary numbers, I must start with the signed and unsigned value, 1's complement and 2's complement. So we need to do lots of calculations that involve negative numbers as well. So how do we deal with negative numbers in binary system? Well, the most important bit or the leftmost bit is used as a sign. So if the question explicitly mentions that it's a signed binary integer, remember at that point that the leftmost bit or the most significant bit is to be considered as a sign. So if there is 1 in the leftmost bit, it's a negative number. If there's a 0, it's a positive number. Whenever the question mentions it's a signed binary integer or a negative binary integer. Now, if it mentions negative, of course, you don't have to think much. Let's say this is our example. It's a signed binary integer. There's 2 ways of solving this. So there is a method called 1 complement and 2's complement, and there's a direct method. I will deal with both of the methods in detail. So 1's complement and 2's complement method looks like this. You flip each digit. So you convert 1 into 0, 0 into 1, 1 goes to 0, 0, 1, 1, 0, 0. Now you add 1 to the rightmost bit. So if you add 1, this becomes 1. Now you calculate the value. So this is 1, no 2, 4, 8, no 16, no 32, no, yes, there is 64. So 64 plus 8 is 72, plus 4 is 76, plus 77. Now since it's a signed binary number, you add a negative sign, right? And you get minus 77. This is how you show a signed binary number. This part where you just flip the digit is called 1's complement. This part is 2's complement. So when you add the single digit, binary digit at the rightmost part, it becomes a 2's complement. Now whenever question explicitly mentions that you need to convert it into 1's complement and 2's complement, you need to carry this process forward. If not, there is an easier method. So for instance, the leftmost part, since it's the 8th digit, right? So the value of 1 into 2 to the power 8 is 128. It could be 7 digit, 16 digit, but it's a standard norm to show ask question in byte. So assign this a value of 1 minus 128. So you have minus 128 and proceed with the regular values of the remaining bits, meaning minus 128 plus, this is 64, this is 32, this is what do we have here, 32, 16, we have 2, we have 1. So plus 32 plus 16 plus 2 plus 1. This gives us 32 plus 16 is 42 plus 6, 48 plus 2, 50, 51, 128 minus 51 is minus 77. So this is another way you could try to solve a signed binary integer. I prefer this step over the 1's complement, 2's complement. But if the question mentions literally that you need to change it into ones complement, twos complement, do not do this way. You won't get any marks. You proceed with this method, right? So this is it about the comparison, conversion of binary to decimal, decimal to binary, signed and unsigned binary. We'll meet in next video to talk about hexadecimal calculation and how overflows can occur in computational calculation. But before ending the video, I would like to talk about various prefix that is used in computer system. So kibi and kilo. So if you see the general standard way to think of kilobyte whenever there is a byte after kilo is to think 1 kilobyte is equals to 1024 bytes. But as a student of science, it's important that our rules are standard all over our domains. So a kilo must always represent zeros in order, meaning a kilo has 3 zeros. Kilowatt, kilonewton, kilopower, right? Or kg, kilograms. And mega must represent 6 zeros. This could be represented as 10 to the power 3, 10 to the power 6. GB is 10 to the power 9, and tera is 10 to the power 12. But something was missing out with computer science, as a kilobyte meant 1024, a megabyte meant something something. So we've come with a standard notation where kilobyte stands for 1000 bytes, megabytes stands for 100,000 bytes, right? But kibibyte stands for 1024 bytes. Mebibyte stands for some value. Now how do we get it? We get it through 1 times to the power 10. This is kibibyte. 1 times to the power 20 is mebibyte. 1 times to the power 30 is gibibyte. 1 times 10 to the power 2 to the power 40 is tbbyte. So remember this notation as it would help you a lot in your exams. So this is for this video. See you soon. Take care. Thank you so much.